Yes, I do.
So we're ready here.
Okay.
I guess you can see our view from the camera.
Yeah, I mean, I can't see the people in the very back, but I can, it's like it's you have, I
Yeah.
want to move it just so that I can see the people in the back.
Yeah, I think we're avoiding the camera.
Okay.
We could just convince the first three of them to fill up the first row, but that's fine. Okay, I think everybody's looking forward for today's lecture. They had a lot of questions as follow-ups. I think that some of them did the homeworks. Some, I don't know. Should I ask for submissions?
Well, no, I mean, I guess the main point is just to show that for the random walk on the triangle, that in the long time limit, the probability being at every single site is the same, and how it decays to this equiprobable final state. But yeah, I mean, hopefully it was fun, and then you can think about looking at larger graphs.
All right. Okay, so I'll leave the floor to you, and I'll mute myself. And as we did last time, it's going to be 1 hour and a half, and we'll take a break somewhere in the middle.
Okay.
And you can ask questions, unmute microphones. That's it.
Okay. Well, so again, let me just emphasize, especially if I hear that there's questions after the lecture, I mean, please ask them during the lecture or during the break. I'm happy to have any questions you might have. So first point is, let me just give you a little roadmap of what I'm doing. So this is 6 lectures. And what I have in mind to do is I presented some very basic facts about the random walk. I'm going to talk about the birth-death process, then aggregation kinetics, and finally, generative models of complex networks. And the reason for presenting the topics that I'm presenting now is that they provide the tools and the perspective that we can then try and understand non-equilibrium processes in general and complex networks in particular. So that's why I've chosen these very particular topics, because I think they're very simple, they're very paradigmatic, and they're going to illustrate many of the tools that one should use if you're going to work in non-equilibrium stat mech. So last time I started presenting the pure birth process. And so in the pure birth process, what happens is that we have a cell that goes to 2 cells with a rate 1. And the question is, what is the number of cells as a function of time? And so what I showed last time is that the average number of cells is governed by the rate equation, n dot is equal to n, because every single cell gives birth with rate 1. And so the rate at which the number of cells grows is just equal to the number of cells itself. And from this, we're going to get that n dot, or n of t, average value is equal to n at t equals 0 times e to the t. And typically I'll choose 1 particle at the beginning, so this is just e to the t. So it's as simple can be. And so what I alluded to last time is the fact that this basic result is actually quite misleading, because it doesn't tell us anything about the full probability distribution for the number of cells. And so that's what I want to focus on today. So let me call Pn of t the probability that there exists n particles at time t. Just want to see if I'm not blocking the board. So that is our fundamental dynamical variable in the problem, because from the probability distribution, we can determine everything about the time dependence of the number of particles or the width of the distribution, whatever we want. So let's look at this quantity Pn of t. And so this quantity satisfies a master equation, which is the following. Pn dot is equal to. So how does this change? Well, one way it can change is I could have n-1 particles, and any one of them gives birth with rate 1. And so the total rate of giving birth when I have a system of n-1 particles is n-1. So with a total rate n-1, and this happens with the probability Pn-1, I will contribute to the gain of Pn because I'll then increase the probability that there are n particles in the system. And similarly, if I have n particles in the system, if any one of them gives birth, then that's going to contribute to the loss of Pn. And the total rate of loss is going to be rate for each one to give birth times the number of particles times the probability that there are n particles in the system. So that is my master equation that I want to study to figure out the full probability distribution. And so there are two ways to solve this equation. One way is kind of the good old brute force method, which is that you just try and write out the first few equations and solve them one by one and hope that you can actually carry this out to the end. And in this particular case, the model is so simple that you can actually do this program. The other way is going to be the generating function technique that I'll spend much more time on momentarily. But let's just first write out the first few equations to get a feeling for what's going on. So we'll have, for example, P1 dot. Well, there's no way I can create out of nothing a particle. So there's no gain term. I mean, this term doesn't appear when n is equal to 1. And then I have minus P1. And so this is pretty easy to solve. This is going to tell me that P1 of t is equal to P1 of t equals 0 times e to the minus t. And again, I'm always going to take the single particle initial condition. So at the initial state, I'm going to assume that there's one particle and only one particle. So this is equal to e to the minus t. And then I can solve for P2 dot. Let's write out that one. So P2 dot. So there's 2 minus 1. So that's 1 P1. So that's P1 minus 2 P2. And so this is just basic differential equation technique to solve this. So I can write this as P2 dot plus 2 P2 equals P1. And then here I can multiply by an integrating factor e to the 2t. And then the left-hand side is just nothing more than P2 e to the 2t, the whole thing derivative. And you see that when I differentiate this, it'll be termed P2 times dot e to the 2t. Then when I differentiate the 2, e to the 2t brings down a factor 2, and then I have the same thing again. And then when I multiply through by e to the 2t, that's what I get on the left-hand side. And on the right-hand side, I have P1, which is e to the minus t, and so here's e to the t. And so when I integrate this, I'll get P2, e to the 2t, minus P2 at t equals 0, e to the 2t. Well, at t equals 0, e to the 2t is 1, so we don't need that. And this is equal to, when I integrate this thing from 0 up to t, this will be e to the t minus 1. The minus 1 is not in the exponents down here. And so this is 0 by construction, or by definition. And so we have P2 is equal to e to the minus t minus e to the minus 2t. And then we can continue this ad infinitum. And so, for example, P3 dot is equal to minus 2P2 minus 3P3. And since we know P2, we can plug it into here and use method of integrating factor to solve for P3. And we can solve one by one each of these equations, and we'll get the answer. But this turns out that this case is so simple that we can do it by this direct method. But in general, this method does not necessarily work. And so what I want to present to you now is a technique for solving this called the generating function approach. So I want to spend some time demystifying the generating function, because I was told in advance that you've seen Fourier transforms, you've seen Laplace transforms, but you may not have seen the generating function. And I want to try and present, first of all, I want to demystify it, like give you a sense of what it really is, and then show you a simple example of how it works before solving this problem by the generating function technique. So the idea here is that what we're going to do is, instead of dealing with the equation for Pn, we're going to define the generating function. And it's going to be P of z is defined as a summation from n equals 1 to infinity, Pn of t, z to the n. So this quantity plays a huge role in studying a lot of non-equilibrium processes. And so let's focus on trying to understand what is the meaning of the generating function, how do we use it, and how do we use it as a solution method. So bear with me a second as I try to erase. And if you want to ask a question while I'm erasing, just ask.
Are we going to go into why it takes this form or just its uses?
Say it again.
Are we going to go into why the generating function takes this specific form, or are we just going to talk about why it is used?
I'm really sorry, but that microphone is a little bit garbled. So like, I don't quite, maybe Sarah, you can ask the question again. Because you're
asking, are we gonna explain why it has this particular form, or we're just gonna assume it? And
no, well, we're going to assume it, but just give me a minute. I'm going to show you how it's so similar to the Laplace transform. And so it's a very natural way of writing the generating function. Okay, so let's see what I want to say here. Okay, so the generating function. So first of all, given a sequence Fn, so here n is an integer in which indexes this thing, and so this is equal to say F1, F2, F3, ... So the generating function, so f of z, I define it to be the summation from n equals 0 to infinity, and where I put the lower limit is really a matter of taste. And so here I'm going to put it at 0, Fn z to the n. So this is called the generating function. And the crucial point about the generating function is that if you know the generating function, if we could somehow by magic calculate it, then we know the entire sequence Fn. And so the point is that the generating function encapsulates the full sequence Fn. And as we're going to see in a moment, I'll show you a very simple example of the Fibonacci sequence where we can calculate every term in the Fibonacci sequence by this generating function technique. Now, the other point about this is that this is the generating function is roughly speaking the same as the Laplace transform. And so that's part of the reason that we write it in this particular way. So let me remind you what the Laplace transform is. So in Laplace transform, so I'll write this as LT for Laplace transform. So we're given some function of time, and we define the Laplace transform f of s is equal to the integral from 0 to infinity f of t e to the minus st dt. So in the generating function approach, the point is that if we're given a sequence Fn, so here, time is like the index in the sequence. And if I have n being very large, I can imagine when n is very large, that this discrete integer variable n is becoming kind of like a continuous variable t. But you'll see this in just a moment. So the generating function f of z is equal to the summation 0 to, n equals 0 to infinity of Fn z to the n. Now, in Laplace transform problems, we're often dealing with situations we're interested in the behavior of some function of time in the long time limit. And in that case, we see that it's the limit of s going to 0 that really matters, because if I take s going to 0, that means that the decay of the exponential is very slow, and it's probing the behavior of the integrand for large time. So small s corresponds to large time. In the generating function, something very similar happens, because you see that when z goes to 1, then this is like an exponential damping factor. When a z goes to 1, the damping factor becomes less and less important, and we're actually probing higher order terms in the power series representation. So what I want to say then is that for z going to 1 minus, so just approaching 1 from below. So let me write now z is equal to 1 minus s, where I'm assuming that s is much, much less than 1. Not 0, but 1. So in that case, z to the power n is equal to 1 minus s to the power n. And asymptotically, that's the same as e to the minus ns. So over here, I can write this as fn e to the minus ns. And now here we have a discrete sum over indices n, but roughly speaking, this discrete sum is kind of like an integral if we're looking for very large terms. So the point here is that this and this are exactly the same form. So what one sees here is that the generating function is nothing more than a discrete version of the Laplace transform. And so everything that works in Laplace transform technology goes over into the case of the generating function. And so the techniques that work in one will work in the other. So that's sort of philosophically, what is the generating function? So what I want to show now is how to use the generating function to solve the Fibonacci sequence, because that's a sequence that presumably you all heard of, and it's very pretty, and it has a beautiful solution by the generating function technique. So if you have any questions, ask away while I'm erasing. And if not, I'll just keep going. And also, please tell me if I'm standing in front of what I'm writing, because sometimes I can't tell. Okay, so let's do the Fibonacci sequence. So that's 1, 1, 2, 3, 5, 8, 13, 21, dot, 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 dot. And so the rule for generating the Fibonacci sequence is Fn is equal to Fn minus 1 plus Fn minus 2. It's a sum of the two previous. Wow, this got to be careful with having cleaner on the blackboard here, on the whiteboard. Fn minus 2. So that is the defining quantity, and we also need an initial condition, and I'm going to choose my initial condition to be F0. I'll call the first term in the series F0, and F1 equals 1. And so we want to solve this equation. We want to solve this recursion formula. And so the way that I'm going to solve it is by the generating function technique. And so let me define now the generating function. Fn is equal to the summation n equals 0 to infinity. I'm sorry, f of z equals Fn z to the power n. And again, where I choose to start the series depends on how I define my initial condition. So since the process starts with F0, I'll define this to include everything in the series by starting at n equals 0. And so what we do now is just as what we've done before in the case of Laplace transforms or Fourier transforms. We take our defining equation, we multiply by z to the power n, and we make a summation. And from this, we will then get from this discrete second order recursion formula an algebraic equation for the generating function. There's only one slight subtlety here, is that where do we start the series? And the point here is because there's an n minus 2 here, this doesn't make any sense if the index here is less than 0. So we've got to start the series from n equals 2 to infinity. So that's one slight subtlety, but it's just that, this doesn't make sense for F0 because F0 is defined to be 1 and we don't have any recursion formula for F0 or F1. And so now let's look at what happens when we do this process. So on the left-hand side, this looks exactly like the generating function itself, but it's missing the terms n equals 1 and n equals 0. So the left-hand side is f of z itself minus the n equals 1 term. So that's minus f1 times z minus the 0 term, which is minus f0. And now on the right-hand side, what is the first term? So the first term is z to the n fn minus 1. So let me write that as a power of z that I'll pull out. So this will equal a power of z that I'll pull out. And then I have summation z to the n minus 1 fn minus 1 starting at n equals 2. So the very first term in the series begins with, when n is equal to 2, it's z times f. So that means that I have the full generating function, but not minus the 0 term. So so what I have here is f of z minus f0. And then the last term is z to the n fn minus 2 starting at n equals 2. So that means it's f0 z squared, f1 z cubed, f2 z fourth. So it's nothing more than the generating function itself multiplied by z squared. So this is equal to plus z squared f of z. And so now what we've done is we've converted this second order constant coefficient linear recursion formula to an algebraic equation that is easy to solve. So we have f of z is equal to. So first point is f1 is 1, f0 is 1, and here I have z f0, which is also 1. So this term cancels that term, and f0 is 1. And so what I'm going to get with just some simple algebra is this is equal to 1 over 1 minus z a second. So this is equal to 1. So 1 and so this canceled 1 minus z squared. Yes. So isn't that amazing? The full generating function is encapsulated in this very simple quadratic polynomial. And let me write this for later convenience as 1 over, with a minus sign, z squared plus z minus 1. And so what we need to do to find the Fibonacci sequence is we just have to now expand this in a power series in z. And there are two ways to do it. One is you can just do a straightforward Taylor series expansion of this quantity for z going to 0. Another way is using contour integration techniques, but in this case, the problem is sufficiently simple that I can just do it by straightforward Taylor series expansion. So the point here is that this object is a quadratic polynomial, so it has two roots, and we can find the roots of this quadratic polynomial by solving this equation. So let's look at the roots. And so that's solving z squared plus z minus 1 equals 0. And so the solution to that is z is equal to minus 1 plus or minus square root of b squared minus 4ac. So that's root 5 over 2. So let's call that z plus minus. So that means that f of z, I can write this in the following way. I can write it as minus 1 divided by z minus z plus z minus z minus. And now we just have to manipulate this a little bit to put it in a form that we can expand it into power series and get all the terms in the power series. So that's what I'm going to do next, after the next. So any questions with anything so far? Okay, so what's going to follow now is straightforward algebra. And it's a kind of algebra that I usually do badly at because I will make a sign mistake. So I'm going to refer to my notes here. So we have f of z. So it's a product of this, and we can write a partial fraction decomposition, and we can write this in the following way. We can write it as 1 over z minus z plus minus 1 over z minus z minus. And then in front, I'm going to have 1 over z plus minus z minus. Yes. Yes. So you can just see by trivial, combining this, that the same quantity is what we have over here. Okay. And so what I'm going to do now is I'll write this in the following way. I'll write this as, with a minus sign here. Again, that's why I'm referring to my notes, because it's going to be so easy to make a stupid mistake. Yes. Okay. So what I'm going to do now to make this simpler is I'll write this as 1 over z plus minus z minus. And then here, I'll write this as 1 over z plus 1 over 1 minus z over z plus. And here I have 1 over z minus 1 divided by 1 minus z over z minus. And now in this form, this factor 1 over z plus, well, that's trivial to make a power series expansion of it. And so we can immediately infer what Fn is, Fn. So by the way, this quantity here, if we look at what the values of the roots are, this thing is 1 over the square root of 5. So this is equal to 1 over the square root of 5. And then I have, when I expand this in a power series in z, the nth term in the series will have a 1 over z plus and a 1 over z plus to the power n. So this is 1 over z plus to the power n plus 1 minus 1 over z minus to the power n plus 1. And now just to get an explicit answer for this, notice that 1 over z plus now comes a little bit of trickery associated with this very beautiful polynomial, which is that if I want to solve, if I have the polynomial z squared plus z equals 1. So 1 over z is equal to 1 plus z. So I just divide through by z. So when I have a 1 over z, I can replace it by 1 plus z. But then 1 plus z, it just changes the sign of the minus 1 here to plus 1. So what we have after all of this is done is we're going to have 1 over root 5. And so we have 1 plus z, which is 1 plus square root of 5 over 2 to the power n plus 1 minus. And so z minus is going to be 1 minus the square root of 5 over 2 to the power n plus 1. And so here's my answer for the value of the nth term in the Fibonacci sequence. Very beautiful, very compact, very simple. And in the limit of large n, this term is negligible compared to this term. And this number inside of the bracket is called the golden ratio. Golden ratio, which I'll define to be G. And so asymptotically, this scales like 1 over the square root of 5, G to the power n. So that is a very elementary example of how to use the generating function to solve a recursion formula. And so what I want to do now is to apply that same kind of technique to solving the pure birth process. So this is a natural spot for me to stop and ask questions, because I'm going to have to erase the board. So while I'm erasing, if you have any questions about this, just ask away. And somebody please tell me if I'm going too fast or too slow, or if this is just right.
No, it's very good. Thank you.
Okay, thanks. Okay, so now that we've seen how the generating function works in a very simple example, I want to apply it to a less simple example, which is the pure birth process. And so I wrote down, and I'll write it down again, the master equation for the probability distribution. And as we saw, that master equation had the form of a differential equation because it was dpn by dt. And on the right-hand side, it was a linear recursion formula. So this is what's called the differential difference equation. And just as in the case of Fourier transform or Laplace transform technology, we try and simplify the equation to some extent by writing it, by introducing the generating function. So that's what I'm going to do now. So our master equation for the pure birth process, I have to be very careful that I don't have any spray liquid on the board because it doesn't, then the marker doesn't show up. So that's why I'm erasing again. So the master equation so that was Pn dot is equal to n minus 1 Pn minus 1 minus n Pn. And so what I'm going to do now is introduce the generating function. I'll define P of z as equal to the summation from n equals 1 to infinity, Pn of t, z to the power n. And notice here that I started at n equals 1, because if I have nothing in the system, there's no way I can create something out of nothing according to the process as it's been defined. So it's natural to start at n equals 1. So let's take this initial equation, multiply through by z to the power n, and sum from n equals 1 to infinity. And let's see what comes up. So on the left-hand side, well, we just have the time derivative of the generating function. So we're just going to have dp by dt. And here I'm writing it as partial derivative because our two variables will be z and t, and we have to be, and you'll see that there will be involved, the right-hand side will involve derivatives with respect to z. So I'm writing this as a partial derivative to emphasize that it's only one of the arguments that's being differentiated. So on the right-hand side, well, there's two terms. Let's look at the second term on the right-hand side because that's simpler. So right-hand side, second term. So what do we have? We have a summation from n equals 1 to infinity of n Pn z to the power n. And so it kind of looks like the generating function, but it's got this annoying factor of n out in front. But what we can do is now do a very standard trick, which is to say this is the same as writing this as z d by dz summation n equals 1 to infinity of Pn z to the n. By this little differentiation trick, we see d by dz would bring down a factor of n, and then it would be z to the n minus 1, but multiplying through by z restores the initial power of n. So now we're treating z as a parameter that we can differentiate with respect to, and in so doing, we can simplify this because we now have that this is just equal to z d by dz p of z and t. So that's the second term on the right-hand side. For the first term, so right-hand side, first term. So we have summation n equals 1 to infinity, n minus 1 Pn minus 1 z to the power n minus 1. Z to the power n, sorry. So notice that it kind of looks like this term, except that there's one extra power of z here. So let me write this now as z summation n equals 1 to infinity Pn minus 1 z to the n minus 1. But the point here is that it doesn't matter, the n is like a dummy index that we're summing over. And it doesn't matter really, there's a term when n is equal to 1, there's a 0 term, but that 0 term actually does not exist because for n equals 1 here, there's no way to start with 0 particles and get to 1 particle. So this term is actually not present for n equals 1. So this series actually begins at n equals 2. So I can change this 1 to a 2. But then the thing is that if I now define a new variable m, which is n minus 1, and this is just the summation z, summation over all m, pm z to the power m, which is just, oh, whoops, sorry, I forgot something here. Let me go back 1 minute. I forgot the n minus 1 here. N minus 1, pn minus 1, z to the power n minus 1. And now everything I said after that is still holds in force. This thing is exactly the same as this summation over here because the first term doesn't matter. And so this we saw gave me z d by dz of p, but there's one more power of z here. So this is nothing more than z squared dp by dz. So after introducing the generating function, our master equation changes to the following partial differential equation: dp by dt is equal to z times z minus 1, because we have z squared from this term minus z from this term times dp by dz. So that is our dynamical equation for the generating function. And so what we've done is we transformed a differential difference equation into a partial differential equation, which is something that hopefully is a little bit more familiar to you. And in this particular case, this is a very simple, although deceptive differential equation, because this is nothing more than the one-dimensional wave equation. And to see that, let me now define a new variable. Let me define z by the following thing: z times z minus 1. Z is defined to be dy. I now define a new variable y by this relationship. And so one sees that by doing this little trick here, this transforms to nothing more than dp by dt, which is now a function of y and t because I've transformed variables, is equal to dp of y and t dy. And this hopefully is something that you've seen before. This is nothing more than the one-dimensional wave equation. And the solution to this equation is very simple. It says that p of y and t is some function of y plus t, where f is arbitrary. Any function will satisfy this wave equation. And then the way that we fix f is by the initial condition. So and is fixed.
Sorry for the interruption.
Sure, no, ask away.
The left-hand side, why didn't we multiply it also by z to the power n?
On the left-hand side here. No, I did. So I just said that the left-hand side was, so let me maybe do one little step here. So we had here pn dot z to the power n, summation from 1 to infinity, which is just the time derivative of the generating function. So you're saying, why do I not have an n there?
Yeah, like how did the z to the power n, like did you just do the summation and then it goes away?
Well, no, it's not that it goes away, but the thing is that z here is just like some parameter. It does not depend on time. So this whole thing here is nothing more than d by dt, summation of 1 to infinity of p n z to the power n. And this thing is my generating function. And so I just have the time derivative of the generating function. Is that clear?
Yeah, okay. So,
okay.
Yeah.
Okay. So to like solve this explicitly, we just have to do a couple of small things. First of all, we've transformed variables from z to y. And by the way, I should say that in all these sorts of reaction problems that you're going to encounter in non-equilibrium statistical physics, this transformation of a recursion formula to a wave equation, this happens always. So even though you might think, well, this is a bit of black magic, like all of a sudden the wave equation appears, it actually is very generic. All these sorts of examples have the same kind of structure associated with them. So to finally solve this problem, what we're going to need to do is, first of all, solve for z as a function of y and vice versa. Then we solve the wave equation, and then we're going to get the generating function, and then we do a power series expansion to extract the physics out of this problem. So first of all, let's look at this guy, because that's what we need. So we have that y is equal to the integral dz z minus 1 over z. And I can write this as dz. And here I'll write this as 1 minus z minus 1 over z. I think that's correct. Yes, it is correct. And so this is equal to the integral. Well, so this integral is very simple. So let me just write it out. So this is logarithm of z minus 1 minus log of z. So this is equal to log of z minus 1 over z, which I'll write as logarithm of 1 minus 1 over z. So here we now have a very simple way of transforming between these two variables, and we'll see that we need this transformation to go from the solution in y space to the solution in z space, which is what we need to then find the power series representation. Anyway, let me just do a little bit more here before I get to that point. So let's look at e to the y. That's equal to 1 minus 1 over z. And so z is equal to 1 divided by 1 minus e to the y. Okay, so now what we need to do to solve this problem is, as I mentioned, so we have the generating function in y coordinates is any function of y plus t, but the any function is actually fixed by the initial condition. So let's look at what happens at t equals 0. P of y at t equals 0. Well, it's just the arbitrary function evaluated at t equals 0, so that's f of y. But now what is the initial condition? And as I mentioned before, I generically will take as the initial condition that my system starts with a single particle. So if the system starts with a single particle, that tells me, and I wish I had more space in my blackboard because my technique is getting all messed up here, but let me just put it over here. So the initial condition, P of z and t equals 0. So it's equal to summation n equals 1 to infinity, p n z to the n. But the only term which appears in the sum is the n equals 1 term, and then I just get z. So the initial condition is z. But now here's a bit of a problem, which is that we've transformed from the coordinate zt to yt. And so we have to express the initial condition as a function of y, not as a function of z. But because the transformation between z and y is very simple, we know what the answer is. So here we have 1 divided by 1 minus e to the y. So let me erase now because it's getting a bit cramped, and I'll just rewrite this. So just bear with me a moment and ask a question if you want to ask. Yeah, so what we had then is that P of y and t equals 0, which is equal to z, which is the wrong coordinate. We want to do it in the right coordinate, which is y. So that's equal to 1 divided by 1 minus e to the y. And now we have the solution for arbitrary time, because as we've seen that the general solution is a function of the variable combination y plus t. So if now for positive time, we just have to replace the y by y plus t. That's all there is to it. So here we have p of yt is equal to 1 divided by 1 minus e to the y plus t. So that is my solution. But from this, we want to find the power series representation of this generating function to extract the nth term. But the power series is naturally expressed as a function of z. So we've got to then go back in terms of the z variable. So here we have the relation between y and z, and now we just eliminate the y in favor of z, so we can do a power series expansion in powers of z. So P of z in t is equal to 1 divided by 1 minus e to the t. And then I have e to the y, which is 1 minus 1 over z. And now all I need to do is expand this in a power series in z. And so let me just do a little bit of simple manipulation that will make it easy to do so. So let me multiply through denominator and numerator by e to the minus t. And let me also write this as, actually, so let me do, allow me just to write this as z minus 1 over z. So let me multiply through by e to the minus t and also by z. So here I'll have a z. And downstairs I'll have z e to the minus t minus 1 minus z. Is that right? Z e to the minus t minus, sorry, I got it. It's backwards. This is minus z minus 1. And this I can write as z e to the minus t. And this I'll write as 1 minus z, 1 minus e to the minus t. And now this is in a form that we can expand in a power series. This is nothing more than z e to the minus t, summation from n equals 0 to infinity of 1 minus e to the minus t to the power n, z to the power n. So we have our final result, and I'm going to stop when I write this result out. So from this, we want to extract the kth term in this power series. It's just the k minus first term of this combined with this, because here there's one extra power of z. And so what we're going to get is that Pn is equal to e to the minus t, 1 minus e to the minus t to the power n minus 1. So that's my final answer. So I think this is a good place to stop because I've done a lot of derivation. And so maybe there's some questions or maybe not, but maybe this is a good place to rest. So what I'll do next, like in the next, after 5 minutes, is that I'll investigate what are the physical properties of the solution. And as you're going to see, even though this looks very simple, the properties are quite amazing and quite surprising. So break time now. And any questions, just ask away. I'm here. So Sarah, maybe you can give me a sense of just, is the level okay, or am I going too fast?
No, I guess the physicists are following for
Okay.
sure.
Okay, great.
The engineers as well, they're raising their thumbs up.
Okay,
I guess
great.
a little bit on the computer science end is kind of a bit slow, but we'll manage.
Okay, very good. All right, so I'll start it again at like in 4 minutes.
All right, so we'll take a break. You can.
Okay,
Thank you.
sure.
Guys, we're back. Thank you, Professor Redner.
Sure. And if there's any questions before I stand up and start talking, just ask away.
Yeah, I think they were comfortable. The physicists were okay. The engineers, maybe the computer science have to scratch their heads a bit, but it's going fine.
Okay, very good. So you tell me when I should start.
I mean, everybody's back and they're
Okay.
back to their seats, so we can start.
Okay, very good. So I derived the solution for the probability distribution. So let's now try and get some physical understanding by probing the features of this probability distribution. And so there's a couple of basic properties. So, okay, basic properties. So first one is that this is a monotonic. It has monotonic decay. Because for any positive time, this quantity, which I'll call A, is less than 1. And so as I go for larger and larger n, this is getting progressively smaller. So that says that the most probable state is n equals 1. So most probable state is n equals 1. So if we were to plot this distribution as a function of n, Pn of t, well, it's actually kind of hard to draw because it's so, you will see in a moment that it's extremely broad. So maybe I should plot versus logarithm of n. And so it's something which is decaying monotonically. That's the crucial point. So the most likely event is that you start with one cell and the cell is lazy and just decides not to reproduce. And so you just have one particle in the system. So that's point number 1. Point number 2 is if we calculate n average from the distribution, we better get e to the t. So let's check that we're going to get e to the t. So n average is equal to summation n equals 1 to infinity of n Pn. And so that's equal to the summation from n equals 1 to infinity n e to the minus t. And to save space, let me write this as a to the power n minus 1. And now I can do a little bit of trickery to like evaluate this, using kind of tricks you learn in elementary, I don't know, calculus, I guess. So this is nothing more than e to the minus t, and I'll just make a differentiation with respect to this parameter a, which is fixed, but I'll treat it as a parameter now. This is the same as summation from n equals 1 to infinity of a to the power n, and d by dA. And you see that if I differentiate with respect to a, I'll get n a to the n minus 1. So this is the same as this. And so this is going to be e to the minus t, d by dA. And then this is going to be a divided by 1 minus a. And then I differentiate this, and I'll get a term 1 over, okay, e to the minus t. I'll get a term when I differentiate the numerator, 1 minus a. I'll get another term where I differentiate the denominator, and I'll get a divided by 1 minus a squared. And I combine these things, I get 1 over 1 minus a squared. So I get e to the minus t divided by 1 minus a all squared. But 1 minus a is just e to the minus t. And so e to the minus t, 1 minus a is e to the minus t. So e to the minus t downstairs is e to the plus t upstairs, but there's 2 powers of it. So this is e to the plus t. So as advertised, we get what we expected from the very beginning, that the average number of particles is growing like e to the t. So even though the most probable event is n equals 1, so here this is at, n equals 1 is the most probable event. The point is that this distribution is so broad that the average value is growing exponentially with time. And one way to characterize the breadth of the distributions, let's look at, say, n squared. And so I won't do this calculation. I'll leave it for you to do, but it's the same kind of thing as here. One can write the summation n squared is summation n squared Pn. And so you have n squared e to the minus t, a to the n minus 1. And then by doing appropriate differentiations with respect to parameter a, one can compute n squared. And so let me just write down what the answer is. The answer is e to the 2t. It's 2e to the 2t, 2e to the 2t minus e to the t, I think. Let me just check. Where is it? Yes, e to the minus t. E to the plus t, sorry. That's what n squared is. And so from this, the variance, sigma squared, which is equal to n squared average minus n average squared. So the point here, n average squared is e to the 2t, but it only cancels one of the two e to the 2t's here. So this is of the order of e to the 2t minus e to the t, which I can write approximately as e to the t in the long time limit. And so the square root of the variance, the standard deviation, is proportional to e to the t. Sorry, made a mistake here. I'm neglecting e to the t with respect to e to the 2t. So this is e to the 2t. I take the square root, I get e to the t. So the point here is that the variance is of the order of the average value. And what this means is that we have a wide distribution. So this is in contrast to, say, like the good old random walk, where we say that if I'm making a biased random walk and I have an average velocity v and I have some diffusion coefficient, then if I move a distance vt, the variance or the spread around x equals vt is of the order of the square root of t. Here, the width of the distribution, so somewhere, way out here, make this a little bit longer, somewhere way out here is n average. But the width of the distribution is also of the order of n average. So the fact that the width is the same as the average value tells you that this distribution is very unusual in its character, because the mean value doesn't really characterize a distribution in any meaningful sense. So it's very important to keep in mind that when you have wide distributions, it's the moments of the distribution that are necessary to fully characterize a distribution. What else did I want to say about this? Yes. The other point is, so that was 3. So point number 4 is the scaling form of the distribution. So as we're going to see in both this example and in later examples, it's very revealing to try and put the distribution in what's called the scaling form, where there's one natural scaling variable with which everything can be characterized. And so let's look at this a little bit more carefully, this original form here. So we have 1 minus a small quantity to the n minus first power. And so 1 minus a small quantity we can write as e to that minus that small quantity. So what I'm going to, it'll be easier to write it out than to just say it again. So here we have e to the minus t, 1 minus e to the minus t to the power n minus 1. So this thing is like 1 minus epsilon. For a long time, the exponential here becomes very small. So let's write this as 1 minus epsilon. And so this I can write then as e to the minus epsilon, where here epsilon is e to the minus t. So in the long time limit, this goes to e to the minus t, e to the minus epsilon, which is e to the minus t, and raised to the power n minus 1. But in the limit of long time, large n behavior, the difference between n minus 1 and n is small. So I'll write this as just n e to the t, n e to the t. So this is what's called a scaling form. And the reason I call it a scaling form is you see that this distribution, it's a function of n and t in principle. But in fact, you see that it's not a function of n and t arbitrarily or separately. It's a function of a very special combination of n and e to the t. So let me call here. Sorry, I have a sign mistake. Yes. Sorry. We have e to the minus t. And then I had e to the minus. There was minus here, so there's minus, and then now I'm replacing n minus 1 by n, so n, and then epsilon is e to the minus t. So this is okay. So this is what's called a scaling form. And the reason I call it a scaling form is you see that n and t don't appear arbitrarily, they appear in the natural combination n e to the minus t. So let me define here from this, let me infer there's a characteristic size scale of my distribution, n star, which is equal to e to the t. That's sort of the typical number of cells that I expect at time t, or the average number. And so this goes to 1 over n star, e to the minus n divided by n star. So now you see here that distributions at different times can be brought into the same functional form by plotting it not as a function of n and t separately, but as a function of n divided by n star. The natural variable is n divided by n star. So this is what's called a scaling description of the distribution, because we found that there's a natural variable n star, which grows like e to the t, and then the distribution can be written as a function of n divided by n star. And the prefactor out in front ensures that this distribution is normalized, because if I want to compute the integral Pn of t dn. So that's the probability that there's any number of particles, cells in the system. Well, that distribution better equal 1. And you see that this thing here, 1 over n star, e to the minus n divided by n star dn, well, that manifestly makes this, if this integrand of the order of 1. I mean, it no longer has any time dependence in it. And in fact, this is exactly equal to 1. So this is sort of the physicist's way of looking at the distribution, which is to try and write it in a way that exposes like what are the basic variables of the problem. And that the point of this scaling form is that if I look at the distribution at time 1 or at time 100 or at time 1,000,000 or at time 1,000,000,000, when I write it in terms of the scaling variable n divided by n star, those distributions will all look exactly the same. So let me just do one more thing here, which is redoing this plot. So if I'm plotting, say, Pn of t, and so this is kind of a cartoon because I can't really represent such a broad distribution easily, but at early times, it looks something like this. At later times, it looks something like this. I hope you can see the red and tell me if you can't. And it's still later times, it looks like this. So this is like early time. This is intermediate. And this is long time, late time. So instead of plotting this as a function of n, one plots it as a function of n divided by n star, the same distribution, if I plot now n divided by n star, which is explicitly a function of time, Pn of t, what one is going to find is early time looks the same, intermediate time right on top, and late time all on top of that. And so this, when you see this feature of what's called data collapse, it's a very satisfying sense that you've sort of understood what are the basic variables in the problem and what is the right description to make the distributions all lie on top of each other. And if this is sort of the way of like developing an understanding of what's happening. And we'll see this scaling form appear in other contexts momentarily. So that is everything I wanted to say about the pure birth process. So ask a question if you have it, otherwise I'll turn to the birth-death process.
We're okay.
Pardon me?
We're okay, no questions.
Okay, great. Okay. Okay. So now a somewhat more physically relevant example is the so-called birth-death process, because this is what happens in all kinds of biological systems, that organisms give birth, organisms die, and when interested in what is the population distribution as a function of time. And so that's embodied by the birth-death process. And you're going to see that very quickly we can solve everything here just using the tools that we learned for the pure birth process. So in the birth-death process, if we have a cell, it gives birth to a daughter or a son, depending, with a rate lambda. Whereas a cell goes to death with a rate mu. And we want to ask, like, what is the population distribution of this system as a function of time? And so once again, we can write down a master equation for the evolution of the probability distribution, so Pn of t. So it's very similar to what we've done before. So how can the probability that there are n cells in the system change? I can have n minus 1 cells in the system. Each one gives birth with rate lambda. The total birth rate of the population will be n minus 1 times lambda. And the total probability of going from n minus 1 to n then will be lambda n minus 1 Pn, the probability that there are n minus 1 particles in the system. And this will be the rate of gain of n particles in the system. And then there is a loss term. Actually, let me put it over. Let me put the other gain term over here. There's also the possibility that I have n plus 1 particles in the system and one of them dies. And the total death rate of the population will be n plus 1 times mu. And then the rate at which, or the probability that that there'll be n particles in the system will then be mu n plus 1 Pn plus 1. And finally, there is a loss term because if I have n particles in the system, any one of them can give birth or any one of them can die. And so the total rate of leaving, the probability that there are n particles in the system is equal to lambda plus mu Pn. So that's my master equation. So you see, it looks very similar to the case of pure birth. In pure birth, there was just this term and this term, but now there is an additional gain term because of the death process occurring. And we want to understand its evolution. Now, it turns out that if lambda is greater than mu, if I look at the equation for the average number of particles, it means that birth is winning out over death, and we're just going to have Malthusian growth. We're going to have exponential growth of the population, and the universe will be taken over by ourselves, which doesn't.
Sorry.
Yes.
Yeah, I think we missed a factor of n in the minus term.
Oh, yes. Thank you very much. Thank you. Yes. N. Thank you. When lambda is bigger than mu, we're going to find that n of t goes as e to the lambda minus mu t. If birth is winning out over death, then there's an overall growth rate that is the net birth rate. And so this doesn't make any sense. For a long time, we have to put in some other mechanism. So in some sense, this is not interesting. Lambda less than mu, n of t, again, asymptotically goes to e to the it goes like, again, lambda minus mu t, and this goes to 0. This goes to infinity. And both of these cases are not interesting because if we start with the population, well, it will disappear in some finite time, and so there's nothing to talk about. So the most interesting case is lambda equals mu. And for the sake of simplicity, let me set that equal to 1. And then our equation of motion is Pn. And by the way, this is Pn dot. I forgot that too. Pn dot is equal to n minus 1, Pn minus 1, minus 2n Pn, plus n plus 1, Pn plus 1. So you see here that what we have is something that looks like a random walk master equation. You know, in the good old random walk, there was a 1 here, there was a 2 here, and a 1 here. So it kind of looks like that. But the point is that the rate at which you're hopping is actually increasing as a function of n. So if you wanted to think of this as a random walk process, it's a random walk on the one-dimensional line, which has no bias because the rate of going to the right or to the left is the same. But it's just that it's getting faster and faster the further away you go from the origin. So it turns out there's actually some very nice parallels between the good old random walk and this birth-death process. So now what we want to do is, just as before, we want to solve this master equation and look at the, solve the master equation and then look at the physical properties of the solution to this master equation. So because it's so similar to everything I did before, I'm not going to go through every single step of the derivation. I'm going to invite you to do it for yourselves, and hopefully it's not too much of an impediment to get to the end of this. But what we're going to do, again, is we're going to introduce the generating function, P of z and t, and this will be the summation of Pn of t, z to the power n. And now there's one little subtlety here, which is that where does the sum start? In the case of pure birth, I started with 1 particle and the number of particles exploded. In the case of birth-death, if the system goes extinct, that's actually an interesting part of the state space. Like, what is the probability that a population will go extinct? So the case n equals 0 is actually now physically significant. So I want to start my sum at n equals 0 to allow the possibility that I can compute P0 of t. What is the probability that the population goes extinct at some given time? So what we do then is we take this definition of the generating function, we take our master equation, we're going to sum it from n equals 0 to infinity and multiply through by z to the n and see what happens. And since we've already seen exactly what happens when I had this term and this term, all we have to worry about is the last term. And I'm not going to belabor this because it's actually quite simple. And so let me just tell you what the result is that you're going to get the following differential equation. dp by dt is equal to z minus 1 quantity squared dp by dz. So that's the result. So again, I invite you, using the techniques we did for the pure birth process, to just do the same steps here. You already know what happens with this term and this term. All you have to worry about is what happens with this term. And after you do a little bit of manipulation, you'll get this partial differential equation. And now we know what to do next is we're going to define a new variable dy by dz over z minus 1 or 1 minus z squared, it doesn't matter. And then we have a relationship, we can integrate this equation to find the relationship between y and z. And we know that the solution to this equation, dp by dy, so that tells us that p, y, and t is some arbitrary function of y plus t, where the arbitrary function is determined by the initial condition. And again, everything follows exactly the same derivation, except for the fact that the relationship between y and z is now given by this rather than what I had in the previous discussion of the birth process. So I'm going to be lazy here and leave that as an exercise for you to work out. And if you have any questions about it, just email me or we can talk, or you can ask later on today or next time. But let me just tell you that if you do all of that stuff, it's actually kind of pleasant calculation. At the end of the day, this is what the answer is. So here is the result. Pn of t is equal to 1 over 1 plus t squared, t divided by 1 plus t to the power n minus 1 for n bigger than 0. Whereas for t equals 0, n equals 0, it's equal to t divided by 1 plus t for n equals 0. So very simple looking result. And what I want to do in my remaining time is just discuss the physical properties of the solution, because they're also extremely striking. So basic properties or basic features. So first point is, you might say, well, now that we have the distribution, we can ask, like, what is the average of the distribution? So let's compute n average, which is equal to summation n equals, and here it doesn't matter if I start at 0 or 1, because I'm multiplying npn. So the term n equals 0 contributes nothing to this. So anyway, so that's what this is. And, so let's see what this is. So again, to make life simpler, let me call this factor here b. And so this is going to be summation from n equals 0 to infinity, n, and then divided by 1 over 1 plus t all squared. And so what is this? This is going to be 1 over 1 plus t all squared. And then this is nothing more than d by db of summation of b to the n. So when I differentiate with respect to b, I bring down a factor n, I have the same power as I wanted here. And so this summation is from 0 to infinity. This is 1 over 1 minus b. And then I take d by db of it, I get 1 over 1 minus b squared. And you see from this form here that if b is t over 1 plus t, 1 minus b is equal to 1 divided by 1 plus t. So I'm going to have 1 over 1 plus t. So I'm going to have 1 minus b squared, but 1 minus b is 1 over 1 plus t, and that cancels the 1 over 1 plus t squared here. We're going to get 1. So the average number of cells is equal to 1. And this is actually, it's sort of obvious that it has to be this way because this process, as I've written here, there's no net bias to it. And in mathematical terms, this is what's called a martingale, that at every step of the process, the average value is fixed. And so this is just showing the martingale property of this stochastic process, that the average number of cells is equal to 1. So, you know, it's like, in some sense, it's obvious, and in some sense, it's quite amazing, because you'd say, well, look, there's all this birth and death going on. You know, isn't there the possibility of having a large number of cells in the system? And the answer is yes, there is, because if we look at n squared, for example, so this is basic feature 1. So basic property 2, if we look at, say, n squared. So according to what we have to do, we want to compute summation from n equals 0 to infinity, n squared pn. And again, you can do the same kind of differentiation trick as I've done over here to write this in terms of a differentiation. And if you do that, what you're going to find is that this is equal to 1 plus 2t. I think that's correct. Let me just check. Yes, it is correct. So what it says then is that even though the distribution, again, it's a monotonic distribution as a function of n, it's decreasing as a function of n, but it's very broad because the width of the distribution is of the order of the average value. So if I look at, for example, the square root of sigma squared, so this is equal to the square root of n squared average minus n average squared. So n squared average is 1 plus 2t minus n average squared, which is 1. So this is equal to the square root of 2t. So the width of the distribution is growing like square root of t. So in some sense, the birth-death process is a little bit better behaved than the pure birth process because of the width of the distribution is only the square root of the average value. Whereas in the pure birth process, the width of the distribution was of the order of the entire average value itself. Two more points, and then I'll be at the end of the lecture today, which is there is something here, a new feature of this process is the possibility of extinction. The extinction probability, well, that's a probability that there are 0 particles in the system. And so that extinction probability is just nothing more than P0 of t. And we see that as t goes to infinity, this goes to 1. So we're guaranteed that even if we start with 1 particle, that the system will go extinct, will eventually go extinct. The point, though, is that it takes an infinite amount of time for it to go extinct because of the fact that this is a very slow decay as a function of time. So this approaches 1 very slowly as a function of time. So P0 of t, if I write asymptotically for large time, I have this is equal to t divided by 1 plus t, which I can write as 1 divided by 1 minus plus 1 over t, which asymptotically goes as 1 minus 1 over t. So as time goes to infinity, you're sure to die. And the last point is, again, the scaling description of the distribution, scaling form. So we're interested in Pn of t for t going to infinity. What does that look like? Well, for t going to infinity, we can forget about the 1 here. So here we're going to get 1 over t squared. And here we have t divided by 1 plus t. And so I can write this as 1 divided by, well, I already have it here, t divided by 1 plus t for the limit of large time. That's going like 1 minus t, I'm sorry, 1 minus 1 over t to the power n minus 1, but in the limit of long time, n and n minus 1 don't matter. And so I can write this as 1 over t squared e to the minus n over t. This is now a scaling form because I see that it's not arbitrary functions of n and t that appear here, but it's a very special combination, n divided by t. And the fact that it's just this ratio means that there is a scaling form that I can write this in the following way: 1 over n star squared e to the minus n divided by n star. So this is the scaling form of the distribution. And what it allows you to do is that you can look at the distribution at different times, and when you plot it versus scaled units, not as a function of n, but as a function of n divided by n star, one has the same form in the long time limit. And so this scaling form, again, is a revealing way of trying to collapse data and synthesize data and see that there's some universal properties of this distribution of a number of particles in the birth-death process. So I'm done for today. And so I can stop and ask if there's any questions, and otherwise tomorrow at the same time.
So I'm asking if they have questions, and I think they don't. And I think even for our physics students, the notion of scaling, you know, data collapse is something kind of new. Have you ever seen this data collapse, where you scale functions and you have them collapse over one curve? I think that all these things are kind of new,
Right,
but definitely understandable. And I see them nod, so we're safe.
Okay, well, yeah, I mean, I appreciate there's a lot of new material here, but I hope I presented it in an elementary enough way that when you look at it at night and just review the notes, everything will be semi-clear. And if it's not clear, then just pepper me with questions at the beginning of next time.
I'll let them speak for themselves, so.
Yeah. Thank you. Thank you very much.
Sure, thank you. You're welcome.
I'm looking forward to tomorrow.
Okay, great.
All right. So thank you so much again.
Okay,
And we're keeping the recording on our YouTube channel for the Center for Advanced Math. So they're even getting a chance to review stuff. So
Okay.
that's also an additional feature of this remotely taught course.
okay, very
All
good.
right.
So see you all tomorrow.
Yep. Thank you so much. Have a good day.
All right, take care.
Bye.